Chonkie. So essentially, the title of my presentation is Hippo's Guide to RAGalaxy. Um, and I'm Bhavnick. I'll do a quick intro because I believe people will be more interested in knowing more about the presentation and what we're doing um, from now. So I'm just a senior machine learning engineer at a startup, a stealth mode startup right now, Yali AI. And I've been working on RAGs and inference and efficiency for about 3+ years now. And Chonkie is my brainchild, which I started about 2, maybe 3 months back, and essentially just something I began with because I was just angry about what was available at that time, and I wanted something that just works for me. But I got a lot of appreciation for it, and it sort of just grew from there. But yeah, so a Hippo's Guide to the RAGalaxy. It's a pun. If you can think of where it comes from, you get some brownie points. Um, but yeah, let's move on to slides. So a bit of a disclaimer before I begin. So yeah, these slides, they're intended for illustrative purposes and they're not for direct citation. So some of these visualizations, they may not, they're just for visualization actually, like they're not meant to be cited. And we get a bit playful with these slides. That's what Chonkie's entire idea was based on. It's just like a bit of just have a fun at times. So even though it's made to be like a good solution. Um, so yeah, some of the things that we'll cover in the slide. So these slides are sort of meant for giving you an idea about RAG in general. There are quite a few questions that people end up having about, okay, is RAG going to be there in the future? What really is RAG, even the first thing? And I do get these questions quite a lot, and I hope I can cover some of these general topics and not just make it an entire advertisement on Chonky. So essentially, the first thing we'll learn about is what is RAG, the why, where it came from. Then we'll have a look into the past very briefly. Then we'll figure out whether we should be chunking or not chunking, or what is chunking. A little about chunky and possibly wrong attempt at predicting the future. Um, so yeah, uh, RAG is essentially just Retrieval Augmented Generation. That's the full form of RAG, and it's just searching before doing an LLM call. So you can search over the web, you can search over local documents, you can search over a database, and then you feed whatever the result is of that search into an LLM, and you give it a query as well, like initially the search query itself, and it'll probably give you an answer. It's sort of an extension of open book question answering, where the LLM has the open book itself, but you actually are doing search instead. If this sort of, if you can make some connections with what is out there, maybe you've used Perplexity before. Perplexity is essentially a RAG over the internet. And if you used something like projects on OpenAI or Claude, that's RAG over that they have a space for putting in documents. That's RAG over specific documents. And I think even Notebook LLM is just RAG. RAG is everywhere, honestly. And some people use Cursor a lot. Cursor does use retrieval in the background to search for appropriate parts of the code, and then they put that into an LLM. So that's also RAG. So RAG is everywhere. And the main idea about why RAG came about was actually LLMs were not meant to be know-it-all models like we treat them to be. So everybody goes to ChatGPT and they ask questions like, "Oh, how do I do this? How do I do that?" And it sort of just knows. But they were just meant initially as language models. They were supposed to understand language, and then you would feed them the appropriate information. They would understand that information and then pass it out and then give you an answer appropriately. So that's how ChatGPT or not ChatGPT, GPT-3, a lot of people use that with RAG. So RAG is sort of preceding even ChatGPT, but it's so, and they were making use of it. So yeah, that's a bit into RAG. But yeah, like you're like, okay, RAG, so what? Why should I even care about RAG? I have I read somewhere on the internet, on Twitter, I mean X, that fine tuning is way better than RAG, and my LLM is like super cool, hyper infinity, lightning pro max attention, you know, laughs in security. There's like a this is what I imagine laughing in security looks like, by the way. So yeah, so you should care about RAG if you don't already think RAG is cool enough. From my examples, it's essentially because RAG, it reduces hallucinations. It's essential because you just this is examples from Mistral 7B with and without RAG, and it's just about what does Chonkie do, and Chonkie is not in the training database. So Mistral actually thought Chonky is a tool for creating large, high-quality images from smaller ones. By the way, which is pretty cool. If I did not make Chonky into like a chunking library, I'd probably make that. But yeah, it doesn't do that actually. So, and on the right side, we see Python library Chonky is designed for text chunking, particularly for retrieval augmented generation applications, which is correct. So that's one way to do hallucination. So you pass in some information. Of course, you only see the question here. And is there a question?
Yeah, I had a question. Or do you want to take questions at the end, or how do you want to?
Feel free to interrupt me.
Is there a type of model that's more suited for RAG? Like, or is this? Can you think of it that way, or is it? Are all model like everything can be used for RAG, but like, is there any intervention that makes it better? That was just curious about it.
There's no actual definition as such of like a model that's better for RAG. It's like question answering, right? So question answering, you could have a model that's better for certain benchmarks. But that also is like very dependent on the specific type of questions you're trying to answer and the knowledge of that model and how it answers it and human preference at the end. So as such, there's no strict metric for models that are good for RAG. It's sort of subjective. But if you're seeing like open book text, like open textbook QA, then there are data sets and benchmarks for that. And you can sort of say that a model that's better on open textbook QA would be better for RAG. Yeah. Any other questions? So, okay. Moving on to the next. So essentially source attribution as well. Because of factfulness, you can do stuff like attribute or ask the model to attribute its sources. So let's say you gave it a couple of pages or websites or books, and it can actually do, okay, this answer was generated from the first and the third passage. So like in this example, what are the main advantages of using RAG? It's on the left hand side, it's completely wrong about something about communication, which actually red, amber, and green. That's a pretty cool combination. But yeah, on the right hand side, it's actually about RAG, and it gives it sources and first and third. That was because I gave it the second one was irrelevant. The first and third were related to RAG, and they were just general Wikipedia searches when generating this. And this is with Llama 3.18b instruct. And then increasing effective context length. Again, coming back to the idea of context length. Most models, if you're not aware till now, I'll just give you a brief. So most models have a limit how many tokens they can handle, essentially sort of like words. Um, so most models nowadays, they can handle about 128K tokens, but back in 2020 or 2019, when there was only a few models available, most of them had about 512 word context length, or sometimes even smaller than that, 256. So that would be 256 tokens is pretty short. Um, and even now, 128K, it's sort of equivalent to a couple of books. That's quite a long context. But if like most models, our research has shown that most models cannot actually um, pay attention to every single thing in the context. There's papers like Lost in the Middle, which talk about how stuff gets lost in the middle for a lot of models. And reasoning is tough for it to do for really long context as well. There's reasons for that as because attention gets spread out too thinly, and people come up with these reasons. But just generally, that's the idea. And this is, if you've not seen this diagram before, this is a benchmark called Needle in the Haystack, which talks about if there's a sentence in the middle of, let's say, a haystack or like long passage of up to 200K, if there's a sentence in the middle of it, can it retrieve that sentence properly and then answer the question based on that sentence? And this is a very initial work and very initial test, and we have like much more complex data sets now. But the idea that we're using LLMs for retrieval over 200K context is sort of misguided, um, because that's not what they're meant to be used for. And then that's what I did with BM25. BM25 is something it's a search algorithm. It's not deep learning. It's nothing to do with deep learning at all. There's no active parameters. It's just general. It's a higher level of TF-IDF, if you've seen that. Um, so yeah, and this is what the diagram for sorry, this is what the diagram for BM25 looks like. And it's all green. So that's because it's a retrieval algorithm. And with retrieval, you can actually get something like this. And it's very redundant. And But I feel like this is sort of missed out in today's universe, that where everybody's about hyper attention or lightning attention or whatever, that retrieval can always get you such green grass and it'll always attend to everything. And fun fact, I'd probably like, if somebody's in the audience who wants to test it out, it'd be pretty cool if they can actually test out long context benchmarks with the RAGs, because I wanted to do that for this, but I didn't have sufficient time before. It would be cool to see how much something like GPT-2 with, I think it was 1024 tokens or 2048 tokens, and a RAG can perform on a long context benchmark, like Loco, I guess, is a long context, or long context, other benchmarks. So I'd assume it would be not the worst. Yeah, moving on to what other benefits of RAG is, essentially you can go beyond the knowledge cutoff date, and DeepSeek R1, which has been trending recently, it's also has a knowledge cutoff date of October 2023, which is about 1+ year ago. And it sort of answers something in this form. And yeah, so left is it's not able to answer, right? It's able to answer what Chonkie is. And it sort of it saves money and time because input tokens. And the small difference, if you notice, like if you're really good at spotting the differences on the left and the right, is because 128K that's for 128,000 tokens, and that's 128 tokens. And this is just a illustrative diagram. But essentially, input tokens do cost money, and for like most places would charge you the same amount of money for the input and the output tokens. There's a slight difference in input and output tokens that the way that models process it now. Initially, models would still do causal LM, which is like a interesting thing we can talk about. But now a lot of models also train on prefix. So they take in the input in one go and then they do the next. Some models do that, but and that sort of makes them slightly more efficient parsing input tokens than output tokens. So, but yeah, I'm not sure exactly what DeepSeek R1 does. Like if it does like prefix or CLM for input tokens, but it costs the same. So yeah, if you basically give it less tokens, you're saving money and probably time as well. So probably going to get you faster as well, most likely. So
Excuse
okay,
me, can I ask a question about the previous slide?
sure.
Thank you very much. I didn't understand, for example, DeepSeek R1 plus RAG. I thought that we do pay for input tokens which represent RAG information. So our private source of knowledge. It's also input tokens, right? So I don't understand what is the difference, why we pay less in the second case.
Oh, because it's less number of tokens that we pass in the input.
But how it happens if our RAG,
Okay.
our private source of information, also input tokens?
Right. So with RAG, okay, in this example, I'm just sort of assuming that you have like a huge corpus of books, and instead of doing a retrieval on that corpus, let's say books of 128K contacts, which is the left-hand side, that's all there that you have, but you're not retrieving any small part out of it. You're passing it completely into DeepSeek, which is the left-hand side, versus you're retrieving something or searching on it and retrieving a 128K token land that is relevant to your question. And this is sort of extension to this, where on the right-hand side, if you see it's 128,000, that's 128K, but the actual length of the needle in needle in the haystack is just the sentence, the best thing to do in San Francisco is to eat a hot dog, something of that sort, just like about 10 tokens or so. So if you just do a retrieval and then do an answering on that just one sentence, you'll still get the answer. But you would have to like, if you don't do a retrieval, you have to pass 128K. So that's the what the slide was trying to show. Yeah, hope that made sense. So, okay, so from all this, we know like, okay, RAG is cool, yeah. So are we done with the presentation? I mean, okay, not just, yeah, just one more minute. I mean, probably like a couple more minutes more, but yeah. So now we know RAG is cool. Now what? A brief look into the past. So like we have a look at where did RAG really come from. And this is the oldest paper I could find which used the word RAG. But you could, people in the chat could like update me on like, okay, maybe this is something back before 2020 that actually used the word RAG or retrieval augmentation. But this was the oldest one I could find. And this is an interesting paper. They actually, they jointly trained the retrieval part and the generator part. And back in 2020, they didn't have the models that we have today. 2020 was the time for GPT-3, I believe, or GPT 3.5, and ChatGPT wasn't there exactly, and it's way back. So what they were using was BERT and BART, and both of them have pretty short context lengths. But we'll talk about that in a bit. Essentially, they mention this. So we experiment with RAG in a wide variety of knowledge-intensive tasks. They essentially used Wikipedia articles for some of the knowledge-intensive tasks that they mentioned in the paper. And what they did was they used 100-word chunks to make a total of 21 million documents. and just like basically splitting at 100 words each of an entire Wikipedia article. And then they just used face with HNSW, which is a way to make an index and retrieve, essentially. So, and the thing that they trained in this was the BERT encoder, the sentence embeddings or the embeddings. So point to note is that they split the Wikipedia articles into 100-word chunks. And honestly, this is also the first time I see the word chunks being used in a NLP context in a RAG paper, probably because this is the first RAG paper I could find. Not the first, the oldest RAG paper I could find. But yeah, they use 100-word chunks instead of feeding them the whole. And if you think that the reason for that is because of the context limit, you're probably right. Usually that 100 words would be approximately equal to 256 tokens. If you take the metric as 2 to 3 tokens per word, which is not a bad, it's a good rule of thumb if you want to take it. So yeah, that's 256 tokens. And BERT was actually, fun fact, not trained for 512 tokens, even though its token limit is 512. It was trained on text shorter than 512, something around 256, and then extended to used for 512. So they had like a fine tuning stage, I think. So it actually performs much better from experience as well, performs much better with shorter context around 256 tokens. So, okay, they did chunking because their context was limited, right? So, but now we have some like hyper infinity attention. Should we even do chunking? Like, or should you even care about chunking? And the answer to that is yes. It's sort of like a spoiler, but yes, you should be. And there's a bunch of reasons, but a lot of them are to do with why RAG is really used as well. So like the saves money slide from a couple of like slides ago, that's because of chunking. So let's say like in a world where you sort of do not chunk and you have 50 books that add up to a context length of 128K, and let's say like you're not chunking at all, right? You're retrieving a whole book. That would still lead you to like a really long context, because let's say not splitting it in the middle somewhere to like pages. You can't retrieve pages as such when you're like putting books. But yeah, so saves money is part of chunking, because if you make the chunks smaller or more granular, the less context you have to pass usually. So, and more often than not, a lot of the answer context is not spread out too much over the entire text. So generally, texts do not, or most questions do not ask you questions or reasonings that spread over 128K tokens. It's usually like limited to a very small set of tokens. And that's also something that's noticed in research. So you can actually pass in 128K tokens and get away with it, and get wonderful answers from DeepSeek R1 instead of 128K. Same with time, because again, less amount of input tokens means less amount of time taken to process them. So 128 tokens in the input would be faster, and 128K tokens would be slower. So, and then comes the granularity part, right? So what is too much or what is too little? And how does that affect retrieval? And from experiments, it's been noticed that it's sort of a bell curve where the middle is actually the best part. But if you go too little for retrieval, and you're assuming in RAG it's either a BM25 pipeline or it's a semantic search pipeline where there's embeddings present for you. Too little context, that means too little tokens. Let's say, let's go to the extreme even and say one word, right? One word is for context is too little. And if you encode them and index them and retrieve them, you're sort of retrieving one word at a time. Even if you add the same words 256 times, that will be just like a jumble of 256 different words. And that'll be just not good for your pipeline. And the same way on the extreme end for too much context is that your model would not be able to handle that even. So the maximum retrieval models nowadays are about 8,000 tokens. If you go on the BM25 side as well, you'd still find the more words you have, the more jumbled it gets in the semantic space. And the way that works is essentially, that's what my next slide also talks about, is that essentially when you're doing semantic retrieval for RAG or for anything for that matter, if you have too many words, it essentially becomes that central limit theorem starts to play into effect where every single article of a million token size becomes same as another article of a million token size, because there's only so much you can differentiate when they're the exact same words being used. So that's the idea on extreme end of increasing the context. And somewhere in the middle, some is what you'd want to use. And every model has like a slightly different Goldilocks zone. So of how much the size should be, even for BERT, for example. BERT's Goldilocks zone was around 256, where even longer than that would sometimes result in worse quality retrieval. And shorter than that, you wouldn't get the most out of BERT. So that's on better recall. So you'd want a specific size of documents or specific size of passages for the best usage of your retrieval models. And the same way works for your generator models, because that's the two components inside your RAG pipeline. That's the retriever and the generator. If you add in more advanced RAGs and you have re-rankers, that's the third one. But even that would benefit from having like a Goldilocks zone. But generally, yeah, how does your chunk size affect LLM hallucination or your generator is the same way, because if you, and that's again been noticed by a lot of previous research, that if you have too much context, LLMs hallucinate more. They tend to pay more attention to the sidelining details than the main concept. So add a lot of irrelevant stuff. Maybe like modern LLMs are able to parse that out much, much better, and reasoning LLMs are able to parse that out as well. But generally, previous LLMs, even smaller ones, tend to hallucinate a lot more if you add a lot of irrelevant details. There's also a concept of hard irrelevancy. It's like essentially something that is actually irrelevant, actually false, but it's so hard for the LLM to tell that it's false or irrelevant or hard negatives. So if you add that to the LLM, it will hallucinate more, and that's not what you want for your system. So there's a Goldilocks zone for the generator as well. That's just about right. So okay, so we have like this Goldilocks zone for two paths, and we can't just feed them whatever context that we think, right? And that's essentially chunking. Like you want to control or have control over what size information you put into your system to get the most out of it. And yeah, it's just something that's a single word would be too little for the LLM to pass out for complex queries, and too much is also bad. So you need something like a Goldilocks zone. And at the end of it, the chunking cost is nothing. It doesn't cost much time because it quite, for passages of length a million tokens, it happens in order of low milliseconds. So in the entire pipeline, semantic encoding when you're making the embeddings or the LLM, reading up million tokens would be a lot longer than that 1 millisecond or 2 milliseconds it takes you to chunk. So it costs literally nothing in time. It costs nothing in terms of actual compute cost, because again, it's on CPU, it's not on GPU. Chunking is just a tiny little thing that happens. It's a free lunch, so to speak. And if you do it just right, versus if you do it terribly wrong, you can see massive gains in terms of your quality of output. So it's this universe where you should, it's sort of essential, I would say, to get a good system going for RAG, especially if you're using RAG already. But if you're not, you should use RAG, and then you should use chunking. Yeah. But okay, so now we're at, okay, chunking is cool because chunking leads to all these benefits that I talked about, and RAG is cool because that leads to more benefits that I talked about earlier, right? So now what? How do we chunk it actually? And that's where Chonkie comes in, where Chonkie is just an opinionated library for chunking, opinionated from how chunking should be like. It should be like fast, it should be lightweight, it should be extensible, and it should be ultra simple. It's like, or at least it tries to be ultra simple, such that very little documentation is needed for it. It's apparent out of the box why or how you would use it. Of course, we do documentation. Can't avoid it, no matter how much I try to. But yeah, that's what it tries to be. And there's a lot of reasons why what was out there before I built it was just not doing one of these things. And I do talk about it extensively in the concepts page as well. But yeah, if you need something fast, because you don't want this to be taking time in your RAG pipeline. And RAG is more often than not, it's search. And if you know something about search, is that it needs to be fast. Chunking is something that's applied during ingestion time. So there's a split between when it's applied as well. And there's something called ingestion time, and there's something called inference time in the search space, where something that's applied on ingestion time is sort of free, and something that's applied on the inference time, that's what you'd want to minimize. So ingestion time is something where chunking is applied, and since it's an ingestion time, a lot of people believe that chunking should not necessarily be fast, but that also does not mean that it should be made more inefficient. So that's one of the reasons why a lot of the market, actually, like a lot of the alternatives, were not doing a lot of things for efficiency because its chunking is applied at ingestion time. Whereas that limits your applications for what you'd want to do. You also don't want to be slow generally if you can be fast. But applications in terms of real-time chunking, in terms of scalability, a lot of these things are limited if it's not fast. And an instance of that would be, let's say you're doing perplexity, right? You'd want to be really fast when you're building something that does internet-based search, and then chunks on the fly, and then retrieves some relevant passages of the websites, and then does the answer generation. So you'd want chunking to be really fast. You want it to be lightweight because why would you want a heavy package if you can avoid that? And generally, like most other packages were much more heavier than they needed to be. You want it to be extensible for general purpose rules. If you want it multilingual, it should be you should be able to add multilingual chunking. If you want it for new application, if you want it for a completely different application, like dataset creation or audio chunking, you should be able to extend the same thing to that application space. And you want it to be simple. So that's something generally you don't want to spend time reading up documentation or wondering how to use something. That's one of the biggest icks I had with the other library. There was just maybe it's just my skill issues, but I just could not figure out how to make the most of them easily. And so, yeah, generally this is how you would want to use chunking. It's just install pip install Chonkie. You would just import a chunker from Chonkie, in this case, recursive chunker, and then you sort of initialize it and use it. It's made so that it's a very, very tiny section of your entire code. And that's how the idea of chunking was. It should not be like a big section. It's just a tiny section that gives you gains for your pipeline. And we can have a deeper look inside as well about what chunking is doing and how to think about chunking generally, and why I believe it's a great space to get a lot of free gains out. And Chonkie thinks about it a lot. I think about it a lot as well. So available chunkers in Chonkie right now are these 6. They're actually about 7. There's one missing from here, and I'll talk about it in a bit. That's token chunking is essentially splitting on tokens. Like let's say you have a limit of 512 tokens for your like pipeline. You just sort of splitting at 512. And one easy thing you can think of is that a lot of tokenizers or subword tokenizers, BP, WordPiece, all of these are subword tokenizers. That means it is very much possible that when you're having passages, that at the end of the passage, you're splitting at the subword. And there's actually like a missing piece of word there that could be harming your entire chunk quality. So that's one thing that token chunking is notorious for, is that while it is the fastest chunking mechanism out there, which it is, it's missing out important pieces at times, and it's sort of randomized in that there's no structure to it. It doesn't adhere to any full stops or exclamation marks, or there's no semantics around where it should be stopping. Token chunking is just fast, easy way to do chunking. It's something that they didn't even use in the paper probably. They used word chunking, where you saw 100 words, right? So they basically chunked on words because they didn't want to miss out on this subwords that token chunking does. But the issue with word chunking that token doesn't have is that word chunking is also pretty slow compared to token chunking. And you're more limited on tokens usually, not on words. Like all contexts are limited based on tokens. So that's one issue with word chunking. But otherwise, it does make a better chunking mechanism because you're not splitting it subword units. The other thing is sentence. And surprisingly enough, when you're doing sentence, based on some heuristics around sentence endings, then you're actually getting it much faster than word. And it's also much more structured because you're not splitting in the middle of a sentence. That means each sentence remains intact. And that's a lot more structure than you could get out of token. And generally, sentence makes a very good beginning point. The next great beginning point is recursive that I used in one of the examples before. And what recursive means is that it goes from high to low on the structure that you define for the recursive chunking. Let's say you have like a markdown document and there's headings of different levels. Then it will go from like highest level of heading and to smaller level till it splits apart each thing into something that's equivalent in terms of the token counts. And it splits and then merges, sort of like works very similar to if you've seen like merge sort. It splits first and then merges to make it of like equivalent token sizes. And this is like a very good go-to, like default. You should, if you're trying out chunking for the first time, it's a good idea to go with recursive first. And then the next thing comes is semantic. And semantic was shout out to Greg Kama, who I hope I'm pronouncing his name right, who actually found from a tweet, I believe, that we should actually have some sort of dynamic way of chunking based on what sentences just go together, basically topical sentences, so to speak. So if there's a long passage on an article, some passages would talk about a singular topic that might be different from the next particular passage, that might be different from the next particular passage after that. So it should sort of be dynamic in the sense that each passage could be talking about different things. It could be about different token lengths as well. And you want to split out where the semantics of that passage end, rather than at, let's say, 256 tokens, very simply. So, but the way that Greg does it is, and we also do it, is there's sort of like a windowing in which we judge for each sentence whether that is included in the same topic or not. And at the point where it should not be included in the same topic, you notice like a huge difference between the semantics of it. Let's say you're doing cosine similarity. You notice a huge difference between the embeddings for the passage that's already created and the sentence. And that's how semantic works to chunk them together and splits at that point exactly where the semantics differ. And then is the late chunking. It's just not a word late, it's actually late chunking from the paper that came out recently, where instead of like splitting first and then making an embedding, they make an embedding for the entire document first, and then they split out sentences. And that's really good for your retrieval. And the way that they do it is there's something called token embeddings first. If you saw, I won't go too deep into it, but essentially you have something that every sentence embeddings have token embeddings, and every single word or every single token has its own embedding that gets generated from the sentence transformer model. And it sort of builds the token embeddings first for the entire text, so that all the embeddings have this attention mechanism, paid attention to every single thing in long context models. So the embeddings have this idea of what is there 8,000 tokens away. But the chunk will only be about 256 tokens and will be much shorter. So you can actually just have these token embeddings mean pooled and then make an embedding. It sort of becomes a bit more, it's a more complex process, but it gives you better embeddings for each chunk and gets you better retrieval quality. And it's a pretty interesting paper because, again, the idea of free lunch, you get about 2% boost in all recall from late chunking versus not. So, and that they illustrate in that paper as well. And that's over a mean of, oops, sorry.
There's a question in chat also.
Okay. Is this
You want me
visible?
I'll just read it out then. Which of the chunker is more useful in terms of retrieving relevant? Do you want to just unmute, Karthik, and just ask?
Yeah. So, Bhavnick, which of the chunker is more useful, like generally in terms of retrieving relevant information for the LLMs, or in general, which of the chunker would actually get more useful information related to the query so that the LLM can answer more reasonably?
Right. That's a good question, actually. So generally, that's just to rephrase your question. The idea is which can retrieve the best, which chunking mechanism can cause the highest recall scores. And because recall is the metric we use for retrieval, late chunking is great. It's slower, but it would get you the best recall scores. And there's a significant boost, noticeable boost from late chunking. Otherwise, there's also mechanisms of generative propositional chunking, which is very expensive. that I talked about in the meeting right before this one, where in the world or in the universe where you have infinite money, you can use something like ChatGPT to get chunks for you in a propositional sort of way where the chunks are very, very short in size. And that would lead to you getting the best quality answers and best quality retrieval results, because it sort of converts the entire problem into a different problem altogether, where it sort of converts, let's say you have like a huge article, it converts each chunks into just propositions that you should be aware of into single sentences. So it's condensing the information, and that condensed information becomes easier to retrieve. But of course, you need a lot of, it costs a lot in time and in money. So you probably would not recommend it. If you're trying for an application, I would recommend late chunking if you care really about the chunk recall. So, yeah.
Yeah, thank you.
Okay. So next, I talk about token chunking, and these are 4 lines on token chunking. That is how we do it in Chonkie, by the way, and also probably really, really hard to beat. I would even put up a challenge if you can beat this. You get some brownie points. You get if you come up to me, I'll give you and I'll add it to Chonkie. It'll be like a huge PR. But essentially, it's all token chunking is doing is it encodes first, which is the most time-consuming part. Then it takes a step size based on chunk size and chunk overlap, and sort of makes token groups together based on that step size. And once those token groups are made together, then you sort of do a batch decoding. And batch decoding is faster because it uses multiprocessing. You can also do decode in a loop of sorts. So this is how you would do token chunking. And if you notice, it's really, really hard to get anything faster than this unless you encode it faster. And that's the idea I had a couple of months ago, that if only encoding is the slowest part, then if I need to get faster than what is out there already, I need to make a tokenizer that's faster. And that's what led to AutoTick Tokenizer, which is essentially the idea that a lot of these tokenizers that are out there, if you see BPE, word piece, sentence piece, they're very similar. Not the same exactly. They're very similar. And TickToken is this library by OpenAI that does much better than Hugging Face in tokenizers in terms of speed. So what if we could support all the tokenizers in Hugging Face with TickToken and use it? Can we do word piece with TickToken? Can we do sentence piece with TickToken? And BPE essentially. Theoretically, I believe you can do. Of course, TickToken does it in a certain way that it expects certain mergeable ranks and pattern normalization, and it sort of is a good AutoTick Tokenizer is a project built on top of that idea that I believe you can sort of just merge everything into TickToken and use it with TickToken. There are a couple of differences that still come up at the moment of talking, but I believe we can sort that out as well and be exactly the same. And generally, you can see the timings wise, it's about 3x faster when done with single threads and thread, and with 4 processes, it's about 3.5x faster to use AutoTick Tokenizer versus Hugging Face. That's a test done on the Llama 3.2 tokenizer. And if you do the same test with GPT, you'll notice the same thing there. So funnily enough, I actually did this test with LangChain when I was trying to compare Chonkie versus LangChain back in like October last year. And what ended up happening was Chonkie was actually like slower on token chunking initially by like 5x or something. And the difference between that was with Chonkie, I was using like a Llama 3.2 tokenizer with Hugging Face, and LangChain, I told it to use Hugging Face, and I passed in the Hugging Face tokenizer. But internally, it was using a tick token tokenizer for GPT-2, a completely different model. And it was apparently it's really cumbersome, or was really cumbersome, to make it use the Llama tokenizer instead of the GPT-2 tokenizer. It was a pull request from months ago that hadn't been merged at that point of time. So that's how I noticed how different the speeds of tick token and Hugging Face are. And that was entirely, the algorithm was pretty similar. There's not much you can do wrong with 4 lines of code. So the speed difference should not have been there, but it was because they were using a wrong tokenizer. So yeah, auto-tick tokenizer is an effort towards that direction. It sort of essentially at the moment gets, if you're just doing token chunking, it will get you like 99% of the like pathway there. It does end up getting some things wrong, but we'll fix that. It's a work in progress. And I'd be happy to open it up for the community members if they want to help on that end as well. So generally, the chunks you'd get out of it are perfect otherwise. So yeah, while doing auto-tick tokenizer, something interesting that I learned was about this GG symbols, like the capital G with a dot and capital C with a dot. I don't know if how many people in space know about these symbols and have seen them in vocabularies somewhere. In most BP tokenizers, you would notice the symbol behind every single word. And the reason for this is actually it converts directly into space when done with bytes to Unicode. And internally, like something that was pretty confusing to me was this piece of code that's on the left-hand side, where before storing, they do this transformation where a lot of bytes are invisible. As in, if you try to read a byte, when it gets printed out, it'll be invisible. It won't print out properly. So before they store it into a dictionary, into some JSON file, or so that it doesn't get stored incorrectly, they make that invisible byte into a visible format through this conversion, where they do a mapping to actual visible tokens. So this mapping is what results in this G. And when you do like a decoding backwards, it becomes space again. So that was like an interesting tidbit that I didn't know. I had to really search for it. And some 4-year-old post from, I think it was Hugging Face, where I found this little code. So yeah. Then one more thing that we use in Chonkie is token estimate validate loops, which is one of the biggest reasons I would say that we're faster in some of the aspects. So these loops end up being used at the moment. They end up being used in sentence as well as recursive chunking. And we plan to add that into word chunking as well, because that's where it should be used as well. And the idea is just that encoding is still the longest time-taking process. It takes the longest amount of time, right? So the less amount of encode calls that you have, that means the less amount of times you want to count the tokens in a piece of sentence, the faster your entire process would be, right? And the idea is that if you do some heuristic-based combining to make it a candidate or a draft chunk first, and then only use validation, like the counting during validation, instead of like every single sentence or every single bit, then you would decrease a lot on the number of times you call the encode. And that means you get faster. So that's how we do, like, we first estimate the tokens. The estimation is done by a heuristic, which is essentially the median token count for GPT-2 or Llama 3 is around 5 or 6. So I calculated the mean as well, which was around 6.38 for GPT-2 and 6.58 for Llama tokenizers. So we do it at 6, approximated at token characters per token is about 6. And that sort of gives you the upper end of it, where let's say, if your sentence has 100 characters, the number of tokens it would have is about 100 by 6. I picked a pretty bad number, so I can do quick math. Somebody in the chat would do quick maths. It's about 12, I think. Yeah. 1 and 41 or 16, sorry. So yeah, something around that mark. And so essentially, you would estimate that first, and then you would do validation. And when you would validate it, you would get the actual encode count. Hope that makes sense. There's also an optional step in calibration where you can actually just count the number of tokens and number of characters per token and the average number of characters per token. And what that would do is essentially calibrate it so it's better at estimating it. And then the estimations become better, and your validation, you need to do less number of validations for it. So essentially, and another heuristic is that you more or less care about going less than the chunk size, but not more than the chunk size, because if you're less than chunk size, even if you're way less by, let's say, 50 tokens, you're still golden, right? Because your limits are on the maximum chunk size. But if you're more than chunk size, that thing gets truncated by the models or the LLM. So you're sort of good if you have a harder heuristic, as in sort of like a higher count than a lower count for the heuristic or value of the characters per token count. So another thing, that this is one reason why we are faster. Another reason why we are faster is also because we default to static embeddings. And static embeddings are really, really cool. This is not my work. This is work by Minish Labs. They released this thing called Model to Vec, which essentially does, it converts a sentence transformer model with attention layers and feed forwards and all of that stuff into something that is static. It's just embedding bag. Using PCA and ZipF and some tricks, you can get a piece of embedding bag, like just embeddings, that you can use to make your sentence embeddings. So, and the way that they make sentence embeddings is just, it's like a dictionary call. It's O of 1, right? So you would, for each word in a sentence, they would get the sentence embedding from the embedding bag, and then mean pool it, or essentially take the mean out of it, and that's the sentence embedding. So it's extremely, extremely fast because it's just dictionary lookups. So, and good part about it is that you can do semantic chunking with these embedding bags, with these static embeddings, and they would result in very, very good quality static chunks, semantic chunks. So, and from some of my tests, it's essentially equivalent, close to equivalent in quality in chunks as well. So it makes a perfect use case for static embeddings as well. And you can see some of these metrics on the right-hand side, where it says about 14. Oh, I'm way past the time. Sorry. Just take like a quick 5 minutes. So it's 14 minutes. Sorry.
If you want to just continue, just continue. It's okay.
Sure. Yeah, so you can see like 14 minutes with Chonky when it's in default settings. That's with a model to vec model versus the other times, which are 1 hour plus in for the other libraries, and Chonky as well for another model. So it's highly dependent on the embedding model, semantic chunking, how fast you can go. So, and the other benefit that we try to do is extensible. And I use this example of multilinguality. And recursive chunking is very extensible. And that's how it's meant to be. A lot of libraries, they hard code the rules behind recursive chunking, but we sort of keep it free for anybody to add their own rules and use it how they want to. And this is an example of just using the delimiter in Hindi. If you're aware, there's a delimiter for like equivalent of full stop that you can just add as a recursive rule, and it would sort of do sentence chunking in Hindi now. So, and it's just about 3 lines of code for you to do chunking in Hindi. So it's very straightforward to do that with Chonky. And this is how sort of Chonky thinks about chunking. It's not exactly just one single thing in the pipeline. Chunking is an entire, it's sort of like you'd be better off if you have a pipeline like this to get like the highest quality chunks and highest quality output from your pipeline. And it's sort of this pipeline is called, we call it CHOMP, which stands for Chonky's multi-step pipeline. That's the short form. And there are 4 steps that we think of it as essentially chef, which is cooking up your text. And essentially, there are a lot of things that in this text that could be harmful to the chunking application. It could take longer if they're there, like ellipses, for example, are really, really tough to parse out. So if you sort of take care of them one step before, then chunking becomes much faster, and you can get better quality chunks out of it as well. So that's what chefs are supposed to do. They're supposed to cook your food so that you don't face issues, just like how you cook your food, because raw food can lead to tummy aches. So then we have chunkers, then we have refineries. Refineries act very similar to, if you've seen the Anthropic post on contextual chunks, but refineries are supposed to add additional context to each chunk so that recall is improved by that additional context, and same for LLM as well. The LLM understanding is improved from that additional context. So refineries and adding additional context always seems to benefit your system or your RAG, though it does cost you a little because it's at ingestion time. You can make with that cost. So we have support for refineries, and then porters are essentially just making sure that you export out your chunks in the format that you need. And some of these aspects we're working on right now. Some of these have been in like already, some of them are already there in part, like refineries are already there. Chefs and porters are something that's ongoing. And quick look at refinery. This is just what I explained, essentially adding more context so you can get better quality recall. There are some aspects that I wanted to cover broadly, but I ended up overshooting the time. There's a lot of other aspects you can actually read up on chonky.ai. And we'll just have like a quick demo. I promise it'll be very quick. Hopefully, fingers crossed. So let me just share this page. Okay, so let me just run this, reconnect. So this is a quick demo of Chonky and how you can use Chonky in your own systems. And one thing I would like to call out already is Chonky actually makes a very, very small part of it. So I'll end up going through all the other parts of the system and probably like a stack that you can use for quick experimentation that I end up using quite often as well, and just makes things easier. for me to experiment with. So sort of just you can just install things. The first time you install it, it does take some time. So meanwhile, you can just go through the code and let this run. So essentially, you install Chonkie, you initialize all the other aspects. Stuff I end up using Together API because it's easier than deploying stuff on your own. You can just inference them, call them out, and they're pretty good. They have all the models that I would need. We use recursive chunking in this example. So you can see how I did recursive levels. These are for Markdown. So essentially just get headings, split at headings before, then you would split at paragraph levels and then some delimiters for sentence. And if you do like do not have any delimiter, that splits at sentence or splits at token, sorry. And then you have chunker that initializes with the rules and chunk size based on the tokens. We end up using a static model, which is, again, Minish Labs static embedding model that just came out a few days ago. And it's pretty good for retrieval. You should check that out. And we use a DeepSeek R1 tokenizer because, yeah, because we use DeepSeek R1 for this example. Two utility functions. One is just for printing and the other is for creating prompts. And we use docling for PDF support. So the way that this example works, by the way, is if somebody can guess which paper this is, they get brownie points. I guess most people should be able to tell approximately what this is about. But if not, we'll see that paper load up in just a second. Docling is essentially just a conversion tool from IBM that converts PDFs and HTML web pages into Markdown. So, and it's one of the best tools out there. Once it converts it into Markdown, it's sort of easier for us to process it into the system. So if you want to support PDFs or have any applications related to PDFs, it's a good idea to convert it into Markdown or text of some sort, and docling is a good tool for that. After docling converts it, we sort of print it, we have a look at it, and we sort of estimate, or not estimate, get the exact tokens that are contained in the PDF. And from then on, we chunk our text. And the way that chunking works is just this. We initialize a chunker initially a couple of lines ago, and right here. So that's about a couple of lines there, and then we just chunk it. We just call the text on the chunker and we get the chunks out. You can have a look at the chunks after in just a bit. Docking takes about a while, so give it some time. After that, we'll do some retrieval, and then we'll do some generation with R1 and see its answers. But meanwhile, if you have any questions, I can just take that.
Where do you use tokenizer here? Could you please show?
Oh, okay. So for tokenizer, as in the DeepSeek tokenizer, this one?
Yes, I just want to see where exactly you use it.
Oh, okay. So I just use it for estimating the token counts. So to give an idea about, okay, it's working now. To give an idea about how many tokens the entire PDF is. By the way, this was attention is all you need paper. The entire paper is about 9,900 tokens, almost 10,000 tokens. And this is where I use it. So just tokenize it or encode text and length, get the length of the tokens, length of the PDF in tokens. So yeah, then we chunk the text with Chonkie. It's pretty instantaneous. There's about 58 chunks. And we can have a look at the chunks here. We see that the chunks are split at these demarcations. The abstract gets split separately. Then there's introduction as one chunk, background as another chunk, so on and so forth. So it's pretty decent quality chunks. We do some retrieval. The way we do retrieval is we first encode it semantically with an embedding model. So we get vectors and we get items. We initialize an index. I do that through Vicinity, which is a good tool to use. You're just experimenting. Then we have a query. For my case, I just had multi-head self-attention query as a query, like what is it? We do a retrieval at this step by converting the query into vectors, and then we call the index with that vector. We get top four chunks here, and it results in these four chunks split out these demarcators. The first chunk's supposed to be about its captions for images. That is on one page talking about that. The second chunk is the background on self-attention, talks about self-attention, multi-head attention a bit, scale dot product attention, third one, and last one is the multi-head attention section. So that's essentially the top four chunks. And when these are fed into the LLM system, DeepSeek, it already has a response for us, which after the thinking tokens, we get this response. You can see it's multi-head self-attention is the mechanism in the transform architecture that enables the model to jointly process information for different representations subspaces. Yeah, I'm definitely not taking up a job as a audiobook reader, but you get the idea. Yeah, so that's a quick demo for Chonkie. Chonkie, as you saw, makes a very, very small section of the entire demo, actually, probably around 5 lines of code. And that's exactly how I think chunking should be. It should be a very small part of what you're trying to do. It should not take too many lines of code. And a lot of it is abstracted out for you so that it's simpler, essentially, to build something like this. And I built this entire thing about a couple of hours, 2 hours actually, and that's including a lot of the formatting work. You can probably get something working like this in 10 minutes. So that was the quick demo. And for people who are still around, we can probably have a conversation on this, but this is what I think this is my prediction of the future of the LLM space and RAG space. Could be completely off, but this is what I believe at the moment. You can probably also wait for, it's a time capsule moment. We can wait for a couple of years to see. But essentially, I believe because of said examples and the way that attention works, I believe RAG is going to be the norm everywhere. In fact, semantic retrieval should already be present in a lot of places. If it's not present, it's sort of not a great UI already because keyword search is hard. A lot of the times you want to search semantically. And same with generation. If you want to do generation, it should be there with RAG always. And that's already seen ChatGPT adopting search, web search, or Claude adopting web search, or something else adopting web search. They do have like some sort of RAG there. Retrieval, whenever it comes to retrieval, you would have chunking because you want to control the granularity. You want to make sure you have the exact granularity. So whenever you would want to use RAG, you would want to try to use chunking and try to control the granularity of the information you pass on. So as long as RAG is there, it's more efficient to have chunking also there. And chunking and RAG will be there till attention mechanisms go below O of n in terms of time, because it's easier to decrease the n in O of n than to go to O of log n with some mechanism. So that's why decreasing the n in O of n, that's what chunking is essentially. And yeah, everybody likes free lunch and everybody will still like free lunch and in the future. that's how human is. That's a human psychology prediction. And we will need chunking because that's the pre-launch. Yeah. So that's it for my slides. Thank you for coming, and sorry for the extended talk. I'd be happy to take any thoughts, feedbacks, questions.